So here is an example of finding eigenvalues and eigenvectors for a specific matrix 2, 2, 2, 2, 1, 3. Okay? So step one, we find the eigenvalues. The logic behind the eigenvector, eigenvalue issue is that we're looking for vectors v that when multiplied by b end up just being stretched by some amount lambda. This equation leads us to what's called the characteristic equation, bv. I can subtract the lambda v from this side, leaving me with a 0 vector on this side. I'm going to draw a line here. I can introduce the identity matrix. The identity times v is still v, but the advantage of using the identity matrix is that when I factor out the vector v from both sides, I'm left with a situation where I have a matrix. I have a matrix times a vector equal to the 0 vector. The only way to have a non-trivial solution, something other than v being 0, 0, which will work, is if the determinant of this matrix is 0. And so for non-trivial solutions, so when v is something other than 0, 0, we require that the determinant of b minus lambda I equals 0. This is called the characteristic equation. And it leads to what we'll be calling the characteristic polynomial. So I'm going to make my line a little bigger. I want to keep this all on one side. So now, taking our work over to this side, what we're looking at is the determinant. Well, b is 2, 2, 1, 3, minus lambda I, that's just a lambda, 0, 0, lambda. I'm going to take the determinant of that, and I need for it to be equal to the scalar 0. So this is the determinant of 2 minus lambda, 2, 1, 3 minus lambda. Taking a determinant, we multiply the diagonals and subtract. We get 2 minus lambda times 3 minus lambda, multiplying this diagonal. And then we subtract what we get when we multiply this diagonal. That's how we compute a determinant. And so we subtract 2, we get 0. Multiplying out, I have a 6. I have minus 5 lambda. I have a lambda squared, and I have a minus 2. Putting it all together, I have a lambda squared minus 5 lambda plus 4 equals 0. This factors as lambda minus 4, lambda minus 1. We have 2 eigenvalues. Sorry, 2 eigenvalues. Lambda 1 is equal to 4. It doesn't matter what order I do this in. Lambda 2 is equal to a 1. On the next screen, I'm going to find the associated eigenvectors for these two eigenvalues. Let's see if we can get to another go. All right, so so our matrix B, again, is a 2, 2, 1, 3. So in step 2, we find eigenvectors. Bad writing. Vectors for each eigenvalue. So I'm going to clean that up a little bit. And again, I'm going to draw a line because there'll be a lot to write. So in this case, we know that B times V, we're going to use the first one, lambda 1. So we're going to try to find eigenvalues corresponding to that. Filling in our numbers, remember lambda 1 was equal to a minus 4. We just found that. And so we have a 2, 2, 1, 3 times V is equal to a minus 4 times V. But V is just a vector of components x and y. So this leads to 2, 2, 1, 3 x, y minus 4 x, y. At this point, we leave our matrix form. We express this as a system of two equations and two unknowns. I have 2x plus 2y has to equal minus 4x, and an x plus 3y has to equal just a y. Moving the minus 4x to this side and moving the y to this side, I get two redundant equations. I'll have a 6x plus a 2y equals 0, and I'll have an x plus a 2y. I don't like this. Let's see, 6x plus 2y, I like that. And an x plus a 2y, I like that, but they're not redundant. Let me just pause it for a second. I realize I forgot to put a minus 4 here. Makes a big difference. And so my minus 4y gives me a x and a, still it's a problem. Well, I'm just going a little too quickly. I see that the eigenvalue is a positive 4. So that's why our things weren't working out properly. Okay, so these should be positive 4s. And now we should get two redundant equations. I'm going to just cross these out, clean things up, rewrite our system as follows. When I bring the 4 over, I get a minus 2x plus a 2y, and that's equal to a 0. When I bring the 4y over, I get just an x minus a y, and that equals 0. Both of these equations are saying that x has to equal y, which leads us to the eigenvector where my x and y components are the same, so I can say it's x times x, or just x times 1, 1. So anything that lies in the 1, 1 direction is an eigenvector. So this is my eigenvector for lambda 1 is equal to the number 4, okay? And just as a quick check, I claim that anything in the 1, 1 direction will be stretched by 4 units. So let's just take 2, 2. Here's our matrix. And let's choose something other than 1, 1. Let's say 3, 3. Let's put in a 3, 3. I guarantee you that this will go to 12, 12. 2 times the 2 times the 3 and the 2 times the 3, of course, give us a 6 and a 6. That's a 12. And the 1 times 3 gives us a 3, and the 3 times 3 gives us a 9. Again, 12, 12. So sure enough, the result is just 4 times what we started with. And we can argue that this is our eigenvector for this eigenvalue. On the next screen, I'm going to do the same thing, hopefully without error, for lambda 2 equal to the number 1. So this time it'll go a little quicker. 2, 2, 1, 3 is being multiplied by xy. And that is supposed to equal lambda times xy. Multiplying out, I have a 2x plus a 2y. I have a x plus a 3y. And on the right-hand side, I have a 1 times an x, so just an x, and a 1 times a y, just a y. These clean up as x plus 2y equals 0, and x, in this case they're clearly redundant, plus 2y equals 0. Both of these are saying that x is equal to negative 2y, and so my eigenvector would be, whatever I choose for y, I choose minus 2y for x. Factoring out the y, I have a minus 2, 1 is my eigenvector. And any scalar multiple of minus 2, 1 is also an eigenvector. Let's do a quick check. We'll actually use minus 2, 1, so 2, 2, 1, 3 times minus 2, 1. Since the eigenvalue, in this case, is a 1, I should end up with the same result. This matrix times this stretches it 1 unit, meaning it gives back the same result. And sure enough, I get a minus 4 plus a 2, which is a negative 2. And I get a minus 2 plus a 3, which is a 1. So sure enough, that's true. And just one more thing, let's just try something else that lies in this direction. So let's go with positive 4, negative 2. If I take this eigenvector, multiply it by negative 2, I get a 4 minus 2. That should also be an eigenvector, and if all goes properly, this matrix times 4 minus 2 should again give me 4 minus 2. And sure enough, I get an 8 minus a 4, and I get a 4 minus a 6, which leaves me with a 4, negative 2. So I found lambda 1 as a 4, and a v1, its corresponding eigenvector, was 1, 1. And I have found lambda 2, which is a 1, and its corresponding eigenvector, which is minus 2, 1. The eigenvalues are unique. These are the only possible eigenvalues for the matrix 2, 2, 1, 3. The eigenvectors are not unique. I could have used 2, 2 as my eigenvector, 3, 3, minus 1, minus 1. Anything that lies in this direction is an eigenvector. Same thing here too, not unique. Okay, that's it. Thank you.